Dr. Alan Barnard is one of the leading discussion scientists and theory of constraints experts in the world. He's also the CEO of Goldratt Research Labs and joins us now. Dr. Alan Barnard, thank you so much for your time. It's a pleasure to have you at SE Tech 23.
Good morning. Thank you very much. So my presentation today is a really exciting one. We've been building digital twins for a very long time. I'm going to be presenting two case studies today, one for Microsoft's global digital supply chain. Contrary to popular belief, Microsoft doesn't only supply software, as you probably know, but they supply a very large range of physical products, all the way from mouses and keyboards to Surface Pros to HoloLenses, etc. And we had an amazing opportunity a few years back to be asked by them to build a digital twin of their full global supply chain and integrated that with SAP. We also did a similar project for Tata Steel, and in both of these cases, they were able to receive substantial return on investment, essentially allowing them to breach the gap that they had between the expected ROI from their digital transformation efforts up to that point and what has actually been realized. Just a brief introduction of my company, Goldratt Research Labs. I started a company in 2009 with my co-founder, Dr. Ellie Goldratt, who was the creator of Theory of Constraints and author of the classic book, The Goal. We started the research lab with a very simple vision of helping individuals and organizations make better, faster decisions when it really, really matters. And digital twins are playing a very, very important part in achieving that vision. With it, we help customers answer two simple but quite important questions, which is, how much better can you do, a little or a lot? And it's a hard question to answer in reality without technology like digital twins. The second question is how best to do much better. What is the simplest, fastest way with lowest cost and risk? How do you know which one is best, not generally, but specifically for your environment, but for every SKU location in that environment? And that's really these two fundamental questions that I will share with you how we are using digital twins integrated with the company's IT systems like SAP to answer these two fundamental questions. I want to share with you, just for those that are not familiar with digital twins, what is it, what is digital twins, and why is it so useful, and why is it essentially the only technology that can solve a very specific type of problem? As you probably all know, there's something that makes supply chains, managing supply chains, making reliable commitments and making good decisions very, very tough. And it's called VUCA. What makes life complicated when you're making real life commitments and decisions is volatility, the V for VUCA. And that means that you're going to have variability in both demand and supply. Most existing IT systems require you to put in one number for demand, like a demand forecast per month, and one number for supply lead time. But in reality, the demand varies up and down, and the supply lead time can vary up and down. How does that impact my actual commitments that I've made and the decisions that I've made? It's very unclear if I cannot fully consider that. The second one is uncertainty. These supply chains are very complex. It's very, very difficult to identify what is actually causing issues and what are the full effects of issues. When you have an assumption that big changes will have big effects, you simply can look for big changes. But if small changes can also have huge effects, it becomes extremely difficult to correctly identify causes and effects. Third element is the first C, which is complexity. There's a lot of interdependencies between the parts. It's not just about trying to optimize the parts, and by that I'm optimizing the system. Often the opposite is true, and I'll share with you some examples of that where you are trying to local optimize, and that's essentially coming at the expense of global optimization. So it's very, very difficult to fully consider all the interdependencies, etc. Most of the existing IT systems simply cannot do that. And then, of course, you have constraints. There's constraints around budget, around time, around resources, around compliance. And the last part that makes life very complicated when making commitments and good decisions is that there's ambiguity around competing objectives. We want to be effective and efficient and compliant. Well, depending on which one I'm using as my main goal or reward function, if I'm applying AI, could give me very different results. So the problem that we're facing is VUCA makes it very challenging to make reliable commitments and good global rather than local optimal decisions in real world environments. Unfortunately, traditional ERP systems and other decision support tools like Excel, etc., are simply not designed to fully consider VUCA conditions. And this often results in us either over or undercommitting or making decisions that optimize parts rather than optimizing the system. So local optima at the expense of global optima. The solution is to use the latest generation of digital twins, which allows you to more fully consider all the VUCA conditions when making commitments and decisions. And it achieves this by capitalizing on all the latest advancements in computing power, simulation modeling, best practices that have been developed over time, like theory of constraints, demand-driven MRP, also allows us to capitalize on human intuition as well as AI. So what makes digital twins today so unique and so much better than what we've had developed before? Our own offering called the Supply Chain Digital Twin is a fully self-configurable app. That basically means that the app can build a complete digital twin, accurate digital twin of one part of a company or even a full supply chain, literally within minutes, using data that's already sitting in the company's IT systems, data like demand forecast, product, bill of materials, supply lead times, etc. So literally 10, 20 years ago, it would take us 3 to 24 months to build accurate digital twins. Today, we can do it in a couple of seconds or few minutes directly from the data. The second part that makes the modern digital twins like our supply chain digital twin unique is that it can be deployed in a number of different ways. The most popular way, which is how it was deployed with Microsoft and Tata, is to be deployed as a Java app that can be installed on any desktop or laptop and sitting behind a company's firewall. Alternatively, it can also be deployed as a web app. Other things that make our supply chain digital twin unique is that we already ship it with a full library of all the best practices. So you can select directly if you want to test out what's the best way of managing my inventory. Should I be using min-max, traditional min-max rules, or should I be using a more advanced economic order quantity rules that also consider holding cost and ordering cost, or should I consider more demand-driven rules like DDMRP or theory of constraints? This is essentially now made available as a little checkbox that says I'm going to run 4 scenarios comparing these 4 rules for managing my inventory at a specific location, and it will show me which one gives me the best overall results. Also, as I mentioned, it can consider most, if not all, of the real-world VUCA conditions that enables users to accurately quantify very quickly the impact of demand or supply changes, and also to identify the most optimal response. If it's a negative stress on the system, how best to mitigate it. If it's a positive stress, like suddenly I'm starting to sell more than expected, how best to capitalize it. Amazon Robotics is one of our users. When that Swiss Canal bottleneck happened, they simply opened up our digital twin. They added an event called Swiss Canal bottleneck. They gave their estimate and said, we think it will last somewhere between 3 weeks and 3 months. Press the play button. We simulated thousands of scenarios of what can happen, showing which of their installation projects will be most impacted and what would be the best way of reducing that impact. So it allows you to not just consider real world conditions in a typical mode of a simulation model to build that into your starting conditions, but it becomes a digital twin when you can upload the conditions as it is now or expected to be, press the play button and see what happens. And lastly, what's very exciting is that it can be fully integrated with ERP systems like SAP that allows you to both automate the data import that can generate automatically these digital twins. So if I'm an account manager, I only am responsible for one account like Best Buy or Amazon. I can make a selection inside of SAP to say, this is the data I want to upload, all the products that I supply to this one customer, and it will instantly build a digital twin of that. Or maybe I'm in charge of a single product line like Xbox, and I want to simulate the launch of Xbox, trying out various strategies of how much inventory should I be pushing out into distributors and retailers compared to how much should I be holding back. As I'm reading in that data for the Xbox, it will instantly build a digital twin just of the Xbox. So it's very exciting that not only the importing of the data can be automated, but also the exporting. So if we do generate in our simulation model different configurations for how best to plan the management or what parameters to use for various rules, those can all be exported directly back into the tables of SAP. In terms of overall architecture, so imagine the digital twin is sitting here in the middle. We typically can get the inputs into Excel. Obviously, Excel has got its limitations. So if the records, which often happens, are more than a couple of million, you have to use flat text files to import the data, etc. And those can be received directly from SAP via API or queries to extract the data. We can then also input the randomness that makes the model a simulation, which is around variability, expected variability, or actual variability in demand or supply lead times, as well as any constraints or other dependencies that's not sitting in the data. And then the process owners can pose questions or say what are the type of scenarios they want to run. And the processes that are being modeled inside of the digital twin literally goes all the way from the first tier supplier all the way to the end retailer and consumer and everything in between. And then also incorporating all the best practices like TOC, theory of constraints, and demand-driven MRP. The outputs from these models, you can generate outputs inside of the app to make it very easy for users. At the end of this for Q&A, I can show a live version of one of the digital twins running to show you what can be seen inside. You can also export the outputs into Excel or logs or directly back into SAP. And then running these models, you can typically run these digital twins in 3 ways. You can do a single run where you, for example, have a specific event and you want to see what the impact of this event is and how best to mitigate or capitalize on it. Or you can do sensitivity analysis. For example, if you want to know how much inventory should you be carrying, you can run a sensitivity analysis on 3 days, 5 days, 7 days, 9 days, compare these and see how sensitive profitability and ROI and free cash flow is as you are changing that setting. And then the last part is scenario comparison, where, for example, you can directly compare rules against each other to see which one gives you the best outcome. Let me show you a quick example of why digital twins are so important, even for simple cases. For those of you that have read the goal or remember reading the goal, there was a nice simple example in the goal that Dr. Gold had created. He called it the dice game. And it posed a very simple question. You have this simple factory. It's got 5 processes that are linked together through series. So process B can only work on materials that's received from process A, etc. Each of these processes can do 3.5 per day. How much do you expect this factory to produce after 100 days? Well, if they truly can produce each one of them 3.5 per day, you'd expect to get 350 out. Very simple, very easy to make commitments, very easy to make decisions. But the question is, what if we add real-world VUCA to it? We've added some variability now. So now the output of each process is determined by the throw of a dice. That's where the name dice game comes from. So on average, it can still produce 3.5 per day, but from day to day, it can vary with a uniform distribution between 1 and 6. How much do you think this factory will produce now in the 100 days? So we just added the variability part. Is it 350? Is it 300, 250, 200? Most people will be absolutely shocked to learn that you get about half out of what you got before. And part of the problem was there's no decoupling between these various processes. So if A produced only a 1, it doesn't help. If B theoretically could have produced 6, it would only receive 1. So you're changing that beautiful uniform distribution into a very skewed distribution that is heavily biased towards the lower end. And this is something that happens quite commonly. What's very interesting about this example that I'm showing here, even though it looks deceivingly simple, it's one of the most complex systems because it not only has a constraint, but it has interactive constraints. Either by design or through debottlenecking, we've ended up balancing capacities. So the constraint is moving all the time, making it almost impossible to make any reliable commitments and to decide where to focus improvement on. So this is the first problem, is when you have variability, your ability to make reliable commitments using averages essentially decays towards 0. And the more interactive constraints you have, the more difficult it becomes. Now the question is, well, what if I did put in some buffers in between, inventory buffers, time buffers, etc.? I still have the same variability. How much could I produce now? Well, it does depend on the buffer size. So just adding a buffer of 1 in between there. So if A got a 4 and B had the potential of producing only 3, that 1 can go into the buffer of AB. Just adding a buffer size of 1 already increases your output from about 175 to 200. That's a big jump. Increasing your buffer to 5 will take it from 175 to around 275. After that, it's not increasing your buffer more than that to 6, 7, 8, 9, 10. Doesn't have that big of a difference. But now the next question is, well, what if we wanted to be able to commit to 300? What is the best way of doing that? And that's where the counterintuitive nature of complex systems come in, is that through our development and research and theory of constraints, the very counterintuitive solution is you can increase your output further by actually creating a bottleneck. For example, preventing process C from producing at 6, only running at between 1 and 5 per day, so the average reduces to 3 per day. We'll use the 3 per day to make our commitments. That's the bottleneck capacity using finite scheduling. So we're now committing to 300. But why would the system actually produce more? Well, A and B can still run at 3.5 per day. So it has enough catch-up capacity or surplus capacity to build up inventory in front of my bottleneck to ensure my bottleneck C is never starved. And because D and E can still run at 3.5 per day, which is faster than C, it can quickly clear away any inventory from buffer CD so that C is never blocked. And if your bottleneck is never starved or blocked, the system will produce what your bottleneck can produce, which will be around 3 per day, giving you a boost in throughput and reliability with a very counterintuitive solution. This can only be seen if you're using simulation models. There are no mathematical shortcut to be able to make these predictions and gain these insights. So even in the simple example, simulation modeling is highly valuable to gain insights. So that's just a simple case. Let me show you how to essentially build digital twins like the dice game, but for full global supply chain. So yeah, so this is one of our digital twins that we use to build digital twins, for example, for Ralph Lauren, Nike, and other retailers. So you can see the steps here at the top. So loading in the data, that's actually reading in that data directly from Excel or text files as an export from a system like SAP. Then being able to look at the data. Step 3 is setting up scenarios of what questions you want to answer. Actually, step 4, running the simulation, and then step 5, reviewing the outcomes and making your decision. So when I'm clicking here on loading up the data, as it did that in those few seconds, it's now built a digital twin for example, a store. I can select the type of store. Say we're doing one for a sportswear company like Nike. I'm reading in the data that shows me what their actual performance was last year. So that's some of the data that I read in. I also read in data that shows what the targeted performance is for next year. I can select the products I want to run in the simulation. So this is, I've already pre-filled this small little store that I'm going to be simulating. I can read in all the images. If I click on one of these, it will show me the details of this, the selling price, purchase price, supply lead time, demand forecast, and all the parameters that have been calculated if I was using different rules for managing the inventory, including DDMRP. I then can move on to the next step. I can select what are the policies that I want to use as my scenarios that I want to compare against each other, and then I can run these scenarios, and I can run it in perfect world, which means that I want to see how the rule, for example, min-max or economic order quantity or TOC, works in a perfect world. So if there was no demand variability or supply lead time variability, how will it perform? And then how will it perform in a real world where there's forecast error and variability and lead times? And as I'm clicking running here, in the short time that you see going past, I'm simulating a full year of all the events that's happening in that supply chain. Customers walking into the store, buying products, consuming inventory out of the store, that triggering the replenishment orders up to manufacturers, the manufacturing waiting for capacity to arrive, producing that order and then shipping it out. So I can already see, I've read in their actuals for the same period, about 200% ROI that they had in the previous period. If they switched to min-max, they could have doubled that. You can see the actual rules that they were using at the moment is EOQ. That's why the EOQ results are very similar to the actuals, because that's the rules that they are currently using. But with theory of constraints, they could have increased their ROI from 200% to over 800%. So generating more net profit with much lower levels of inventory. But that's, of course, in perfect world. What will happen in real world? Yes, the performance does go down a little bit, but it's still an order of magnitude higher. And you can see I can compare directly TOC with DDMRP as well. I can zoom into the financial side, and it will generate detailed profit and loss for all the products, or I can select a specific product and it will show me the financial performance for that single product. Most visually kind of descriptive is showing the inventory levels. So the red line was what the actual levels of inventory was that they had for a period. And then we re-simulated that with different rules with min-max. You can see even with min-max, they could have reduced inventories, but with TOC and DDMRP, they would have reduced it dramatically. And I can zoom into there. You can see the difference, a 72% reduction in inventory, and at the same time a 76% reduction in stock out days just by changing the rules. And I can see it for all products, or select a specific product and see how that rule would have performed here. Here you can see in the past they placed big orders very infrequently, sometimes still running out of stock. So having that horrible combination where you both have lots of surpluses and you still have shortages. On this case, they could have reduced inventories by 86% by implementing a theory of constraints rules, and reduced stock out days by over 100%. So that was just a quick demo to show you that's one of the other advances in digital twins, is that we can generate now these digital twins to look like apps, make it very intuitive for users to be able to use and engage and answer these type of questions. I hope that was helpful, just as a quick opportunity to see what's possible with today's technology now. Microsoft contacted me. They were trying to ensure that they can get value from their SAP system. They wanted to change the way that they manage their global supply chain for all their digital products. They call it DSE for digital supply chain. Whatever products they pushed into that supply chain, they wanted to be confident that it will produce those products with the highest level of reliability, the shortest lead time, and the lowest cost and inventory. It's a very complex supply chain. As you can see there, producing over 77 million units, 42,000 different SKUs, 390 different contract manufacturers, a very, very complex supply chain. And the question was, would it be possible to come up with one way, one set of rules for managing the supply chain implemented in one system, which is SAP? And that was the challenge that they gave us. They had a very, very tight deadline. We started the project in 1st of September. I met with the CTO, and he essentially said to me, listen, you have an hour to convince me that you can help us do that, and that with a simulation model, we can validate what's the best ways for deciding on order fulfillment strategies and for deciding what's the best way to manage inventories. If you can convince me, you have the rest of the day to convince my direct reports. And if you are successful in that, we'll start the implementation. I said, when did you want to go live with these new rules into SAP? And they said by mid-December. While we were 1st of September, I was hoping it would be mid-December the next year, but it was mid-December of the same year. So we had just over around 3 months to do this full project. This wouldn't have been possible without a digital twin to quickly validate what are the best rules to use, and then in parallel start implementing those rules into SAP. I have a quick video just of the CTO of Microsoft, Robert Meshew, sharing the results. What Robert shared was within the same financial year that we started the project, we increased service levels by over 5% of implementing the theory of constraints-based rules that we validated first inside of our digital twin to make sure that these rules would be effective in reducing shortages and surpluses without increasing cost. And those rules were then implemented directly into SAP. Not only did the service levels go up by 5%, but they were able to reduce inventories by over $250 million and increase sales by about $100 million by reducing obsolescence and surplus inventory that was taking up space, also reducing the markdowns on those. How did we do the project? We started off with designing a full strategy and tactic tree that shows exactly all the changes that would be needed in how to decide the order fulfillment strategy, how to quote reliable lead times for assembling or bundling to order and making to order, how to ensure sufficient parts are in place for all the finished goods, components and raw materials that were being managed on make to stock basis, how to control the release of this hybrid of various order fulfillment categories using simple traffic lights for buffer status to control WIP, how to achieve a single priority system throughout the supply chain, and also how to systematically improve flow by constantly monitoring what's causing further delays or causing stock outs, and then focusing your improvement efforts and investment on only those elements. So once a solution design were completed, we tested this solution design inside of the digital twin as a low-cost, low-risk way of doing essentially a virtual pilot of what the performance would be like if we changed these rules, and we used their actual past performance as a baseline comparison. So this is what the digital twin looks like. You can see the map showing all the connections of their global supply chains, and this is what the results came out to be. The purple line is what the actual level of inventory was, the middle graph, the actual level of inventory was over that period. The blue graph is what it could have been had they had used the theory of constraints rules that we validated through the digital twin, and that was finally implemented into SAP. So you can see a substantial reduction in inventories. And on the right-hand side, that graph there is monitoring the sales at risk. So because generally speaking, actual lost sales is not being recorded as a hack to quantify the sales that you might be putting at risk by having stockouts or taking longer to supply than what you're quoting your customers. We're calculating what's the sales velocity when there is stock, and we multiply that by the number of stockout days to quantify the sales at risk. You can see the actuals was very high. It was $60 million per month that was sales at risk by stockouts. And with the theory of constraints rules, that has gone down to 0. So not only we are able to dramatically reduce the inventories, but at the same time completely eradicate sales at risk. The actual results that the CTO reported was very close, within a few percentage points of what our digital twin was predicting. So that was the ultimate validation that the model was an accurate representation of their complex environment. When you dive into the details, these digital twins are not just black boxes. You can actually go look inside, look at the stock levels of a specific product location, like in this case, and you can see it highlighting again the difference between the purple, which was the actual level of inventories over the past year, and we reran that period with different rules. The blue line, and you can see we are picking up where the shortages and surpluses are coming from. A very interesting insight that we gained is they had a major challenge of doing allocations of inventory. So imagine you have a client like Best Buy, and Best Buy said we agreed to give them 10,000 per week of a new product that is being launched. Well, the question is, how do you allocate that stock? So if maybe in the first week they're a little bit conservative, they only order 5,000, you will only ship them 5,000, but they have an allocation. So you have to tell SAP to keep that additional 5,000 for them because it was allocated to them. Maybe next week they order 15,000, and now SAP will say, well, you have an allocation of only 10,000, but you still have a remaining allocation of 5,000, and it will ship the 15,000. So at a customer level, unders and overs will cancel out. But what the simulation was showing, it across customers, it wasn't canceling out. So if one customer constantly under orders, you are keeping stock for them. Another customer is over ordering, you short supplying them, not being able to utilize. So that was one of the first scenarios that we tested, which is to say, what if we don't allocate all the stock to customers, but we kept some portion of it centrally that we can dynamically allocate? And the difference was big in this case, an increase in sales of over 40 million just in that single product category. Sales up by 15% because by differently allocating the inventory, we could reduce avoidable shortages for those customers that were actually selling a lot. So this was just one of the scenarios that we modeled in the digital twin to understand and quantify the level of avoidable shortages and surpluses and how best to mitigate that. The second case study is Tata Steel. Tata Steel, when we started working with them, this was Tata Steel in UK. It was shortly after they had bought British Steel. It's a very complex company, Tata Steel, globally, established in 1907. First integrated private steel company, Asia's private steel company, more than 30 million tons per annum, very large, diversified operations, vertically integrated all the way from the iron ore mines and coal mines to actual retailing or distribution of the motor vehicles and other steel products. The British Steel, which was renamed Tata Steel UK, when we got involved, they were not in a good position. They had this perfect storm where the exchange rate was collapsing. against them, squeezing out margins in the UK. At the same time, the recovery after the 2008 meltdown was much slower than expected and didn't fully recover. So they ended up with almost this L-shaped recovery, not a U-shaped recovery. And lastly, because of the financial pressures, they were losing almost £1 million per day. They literally didn't have time. They didn't have any budget, and there was no real ideas on how they were going to turn around British Steel and save it. And as a result, in June 2015, the board of Tata Steel made a decision to close the business. The only question was whether to do it pre-Christmas or post-Christmas. Well, there was a very courageous person inside of Tata Steel that believed, based on the results that they had seen with implementing theory of constraints inside of Tata Steel India, that it was still possible to turn around the company. He had developed a plan, whereas previously the Grey Bull Capital, one of the companies that they were trying to sell British Steel to, said, you know, not only are you losing money, you don't have management team that has any credible plans to ever make money. Why should anybody buy this company? That's why they were planning to close it. After this person, Barnard, was appointed to head up the company as the new CEO, he immediately started working on a plan, and our involvement was using a digital twin to help validate each of the key assumptions of how to move them at that stage. They were losing about 100 million per year back to a profit of 100 million per year. And when the plan was presented together with the digital twin to validate that the plan was actually feasible, the same partner said that I see roughly 300 plans a year. This is the most credible one I've seen in the last 5 years. So that again, just highlighting, if I'm not sure if you could hear the sound, but they were facing difficulties to decide how to improve the company's productivity and profitability. They just couldn't take the risk of making commitments that was not viable, and they reached out to us. We ended up building 4 digital twins for them. One of their full supply chain in the UK, one specifically focused on the hot coil production area that they had major bottlenecks with, one focusing on the steel and slab production side, and one for their specialty steel manufacturing plant that they also had some constraints with. It allowed them to turn these simulation models into digital twins by integrating it directly with SAP. So the main project challenges was how to improve profitability and service levels with very high levels of confidence. They were very concerned, the shareholders were very concerned, because many of the past initiatives and investments that they've made in digital transformations and other improvement initiatives, the ROI was well below expectations. Past focus was mainly on cost reduction, debottlenecking. They wanted to see if it was possible to build very quickly these digital twins. They don't have years to do that. We had to do it within just a few months, and then to use these models to identify primary causes of the past performance gaps, determine the likely impact of making the changes that we were recommending to implement theory of constraints. Many of these insights we knew was going to be counterintuitive, and we wanted to integrate this with the SAP system as an ongoing decision support tool. I'll just show a quick video that shows what these models actually look like. So the first one is the model of the full global supply chain. So as you see, the data is being read in directly from SAP in the form of tables. It's actually instantly building a digital twin of that environment for which the data was read in. So that could be a single product or single region, or it could be all the products and all the regions. And there are multiple way views of the supply chain. You can zoom in, you can click on specific resources, you can actually see the operating utilizations and efficiencies of those resources. We also built a full 3D model of their hot coil finishing. There was a major bottleneck in terms of storage space. When we arrived at the plant the first time, we couldn't find parking because there were steel coils parked in the parking base that was meant for cars, This allowed us to gain insights in terms of why the work in process of steel coils inside the factory was so high that things were just getting jammed up in there and very little was coming out. Part of it was an algorithm that they developed that identified when a customer places an order, what is the most profitable production facility to produce the coil and what's the most profitable way of getting the product to the customer. Well, this algorithm that was put into SAP was causing them to constantly overload some plants and distribution facilities and underload others. We could test a different way of dynamically determining what is the most profitable location that actually has capacity at the time of placing orders. So it gave a completely new perspective of available to promise, and we implemented that, and it had substantial benefits to reduce the congestion and increase throughput. This was a very detailed model of the steel plant 3D model where we tried out different ways of scheduling the casters. Very, very complex mathematical problem to solve. They were doing it essentially in Excel. That is not the best place to do these complex campaign runs. We could try out different options in our digital twin, show them how it would schedule the manufacturing facilities all the way from the furnaces to the rolling plant, and then test those rules that we came up with in a full 3D version of the model, feeding in direct data from SAP and their manufacturing execution systems. So in summary, the business case was there was lots of congestion, long lead times. We wanted to find out what's the simplest way of solving that problem, how to overcome constraints, and we gained incredible insights from these models that could show the people operating it why these problems were happening and test out better ways of improving flow and reducing cost. One specific example that I want to highlight is essentially how the digital twins was used to challenge an existing industry paradigm and related best practice. In the steel industry, ton dishes essentially cost around $5,000 every time you do one heat. So if you make a change to the type of grade that you're producing through the casters, then you have to change the ton dish. So generally speaking, they have always had the rule to say, listen, if one heat is 100 tons, you can't afford to just produce 100 tons. You have to do at least 5 heats. That will be 500 tons to justify making the change and losing that money for the ton dish. The problem was that if your customers only needed 100 and you are producing 500 tons, you are overproducing 400 tons. That consumes raw materials, that impacts your cash flows, it consumes capacity, not just at the caster, but all the way downstream as well. And we wanted to test, well, what would happen to cost per ton? How much will cost per ton actually increase if you allowed the system to just produce what is absolutely needed? And if it only needed one heat of 100 tons, then allow it to only produce one heat. And to their shock and pleasant surprise, actually, it showed that the cost per ton will actually go down by 3%, not up, resulting in a 9% increase in profitability. This has been a paradigm in the industry for many, many decades, and they were only able to challenge it to show that actually trying to save setup cost is a guaranteed way of increasing your cost per ton, not reducing your cost per ton. So just as a summary in terms of some of the key insights here, so going back to how do you bridge the gap in your digital transformation in terms of expected ROI deliveries. Unfortunately, most of the digital transformations have not yet delivered on the full potential that these digital transformations could have, and the digital twin is a fantastic way of being able to unlock additional value. SAP can be used to create or put in all the data that these digital twins require to instantly build accurate digital twins, and the outputs from the digital twins can be fed back directly into SAP to decide on the optimum order fulfillment strategies, optimal inventory management rules, optimal finished goods and semi-finished good buffer locations, optimal sourcing and transportation policies and priorities, and also to make reliable financial commitments, because inside of these models we can generate full profit and loss, balance sheet, and cash flow statements. So in summary, key insights is that supply chain digital twins can overcome the limitation of not being able to fully consider all the VUCA conditions when making strategic and tactical decisions at every level. That dice game shows you that even at a simple level, if we are using averages to make predictions, we will always get it wrong. We just don't know in which direction. Are we over or under committing? The digital twins can also help you to directly compare the performance of any rule in full compliance mode, to see what's the best rules to use for planning or execution or ongoing improvement by product location. It can be used to quickly enhance or test the impact of actually fully automating human decision making, something that many companies are very nervous about. They just don't know what will happen. This way you can test it before going live. Also, it has a very important synergy with AI. AI to train needs a lot of data. Often the data is either biased or is inaccurate or simply not there. So the data sets that you need for AI to train, and digital twins can actually generate that data, very large set of data, much more representative, and do it very quickly. And if AI comes up with different ways, for example, for doing demand forecasting or managing inventories, you can actually stress test these AI generated rules in your digital twin and compare it with simple heuristics like min-max or more advanced rules like theory of constraints or demand-driven MRP. We actually had a case recently where a company had spent tens of millions of dollars using AI to learn how to better manage their complex operations. And we showed them that if they had gone live with those rules, it would have given them worse performance than their current simple rules that they were using at the moment. The digital twins can be used for supporting decision making at all levels, from designing full supply chain networks of where to put in distribution centers and retailers, all the way to very detailed granular level execution decisions. And lastly, you can use it in real time or for long-term constraint and buffer analysis and constraint-based scheduling and optimization. Maybe just something else to mention is that supply chain digital twins, as I mentioned, we've been building them for many decades, but because of the time involved, they were simply so costly. They were typically a few $100,000, sometimes millions of dollars to build. So really only very large companies like the Microsofts and Tatas could afford to have digital twins of their business process or even their full supply chain. What we were able to do with building digital twins now directly from the data sitting in systems, IT systems like SAP, is it's possible to offer these digital twins on a SaaS basis for as little as a few $1,000s a month. So it's made it much more accessible also now to small and medium-sized businesses.
Dr. Alan Barnard, thank you so much for that presentation. We really appreciate you making the time to chat to all of us today at SC Tech 23. Thank you.
You're very welcome. And maybe just a last point on the AI side, what's very, very exciting is we're already working, collaborating with a few partners. Imagine building ChatGPT directly into a digital twin and being able to, as a supply chain manager or VP, being able to communicate in simple English directly with your digital twin and say, we've run multiple scenarios. I'm curious to know, why did we have a stock out in this area? Why were we stuck with a lot of stock? And in plain English, you can then communicate directly with a digital twin, and it will use AI to go and find the answer and come and present it in a format that's very easy for you to understand. So that's the next level that we are already working on. Very, very exciting about the potential of combining digital twins with generative AI. So that's it from my side. I hope that was valuable. Like I mentioned, we have done many other implementations. These are just two case studies that we have the approval because we have presented them in the public domain to share it today. Thank you so much for the opportunity to present it. And I've included my email. It's alan@goldredresearchlabs.com. If they have any further questions, they're absolutely welcome. Open it up for any questions that you might have.